Thanks, Ollie. Now, we're about to have our first keynote of the day. Well, our only keynote of the day, our second of the conference, and I'm excited. Do you know that video of Steve Ballmer from Microsoft, where he runs on the stage and there's sweat flying off his head, and he's running like a monkey, and he's so excited. That's me right now inside. Except I'm British, so you can't tell. I'm really excited to hand over to Josh and Dick to find out more about 4. Thank you.
Thank you. Oh.
So yeah, if you Google Dance Monkey Boy Dance, that video is the top hit, I believe.
Okay. Are we good? Oh, great. Yay. See, Linux can work.
So while we get set up, if someone could Photoshop John's face onto that video, we will show it live.
All right, I think we're off.
Yeah.
Thank you everybody for coming to this. I think when we first talked to John about this, I had this kind of crazy idea that had come up because at work, I'd noticed that there's a lot of, I guess, avoidance or hesitance to use 4, and there were a lot of things that my co-workers they were tricks that they just didn't know it could do. And the whole kind of genesis of the talk, the nucleus of it came from there. We hope that this will entertain you. We further hope that most of you will at least take away one fact, something you didn't know about 4 from this talk. And if you don't, we apologize. Hopefully it won't be too boring.
Yeah, so it's going to start a little light, just things that you've done, and then it'll get a little deep. So
yeah, and there's plenty of puns, and also, I should point out, this is the patented Dick Wall design studio that produced these slides.
Yeah.
You're being treated to a real visual...
Although they had some consulting from the Suereth
visual
studio.
Experience, yeah. It's marvelous.
Yeah,
my very best design skills.
If you guys don't get this pun, this is actually a YouTube link, which we are unable to click on because we do not have internet, so you can't hear the song.
Yeah.
But if you're familiar with War, What Is It Good For, the song, yeah.
We have a couple of visual aids that unfortunately will not load this morning, so we'll put them on the channel later so that in your mind you can use your imagination to insert them at the correct point, and then you'll laugh because it's really funny. So there'll be a delay. You know, it's the gift that keeps on giving.
Yeah, 3 hours later you'll be laughing, I promise.
All right, so the loopy side of the 4s, I think everybody goes through the same kind of learning process with 4 when they first hit Scala. They see a 4, and they're used to it from another language, and they think it's about looping. And that's what they use it for. So, very typically, people start out with some stuff like this. They start out with for I, from 1 to 10, print line hello world. And let's fire this up and give it a run. And sure enough, you get hello worlds. You can do a bit more with it. I, that's set up on the left-hand side in the setup of the 4, can be used on the right-hand side, so you can print the times table. Great so far. Now, here's the thing. In this first one, you're defining I, but you're not really using it, right? And Scala's not real big on making you name something if you're not going to use it. So one of the things you can do, and this is sort of universal, is you can just assign it to underscore. Okay? It still makes it happen. It still does the iteration that number of times. But if you're not going to use it, why name it at all? So just to show that works.
Plus, this makes sure we have about 15 ways of using underscore in the language.
Yes. Underscore always means some kind of thing. That's its mnemonic. It can mean anything, everything, nothing, something, and the thing. I think that's all of the things that I've come up with so far, but I'm big on mnemonics. I like to read things out in my head. Okay, so let's do something like this. Multi-line, of course, in curly braces, you get semicolon inference, so that's good. What is 1 to 10? Well, that's a collection. Now we're going to start to see some of the, initial clues that maybe it's not just loops that we're dealing with here, but 1 to 10 comes out as a range. It's like a lazy collection. If we want to, we can put more than one thingy. We're not going to refer to the G word yet.
Yeah.
That comes later, but we can put more than one thingy in there, and you get the ability to do loops within loops, effectively. And what this actually turns into behind the scenes, and we'll see this in a bit more depth in a minute, is for what we're doing right now, it turns into nested for each statements. And this is actually what happens during the parser phase in the compiler. The for gets turned into a series of chained calls, for each, or as we'll see in a minute, flat map and map. And there's some other things that it gets turned into as well. So I can show you it's exactly the same code, just makes it a bit more readable. You don't get the indentation effect.
This is known as the rocket effect. If
Yes.
you take a look at it,
Oh yeah, sorry.
your arrows kind of form the top and tip of a rocket, and then it comes back. So you have the fuselage at the bottom is the semicolons. So just so you know, rocket syntax is bad. That was of the 70s.
And then just to show, Josh, is this an idiomatic use of fors here?
Let's take a look.
Let's take a look. Well, we're supposed to be functional programmers, and if you look at this, it does something, sure enough, it does something useful, tells us what the times table is. But what we get back, if you look at this, I'm assigning the results of that for to a couple of values, x1 and x2. These things come out with the somewhat unhelpful open-close parens, the empty tuple, or unit, as it's known, and they are of type unit. So
Yeah, I don't really care about units.
no, units, the only thing you can do that's useful with a unit is have some kind of side effect, because you're not getting anything else out of it, so not very functional. All right, so, and now we start with the puns. Anybody get this one? Anybody old enough to get this one? The weirding way from June? Okay, yeah, kind of nerdy.
His eyes are blue.
His eyes
You
are
can't
blue,
tell.
but you can't really tell. Yeah, it's Monads.
Anyway, so this is when you start on your path. You start on the path of learning a different way of telling the computer to do things. And that is not telling it how to do it, but telling it what to do.
Yes. So the yielding way is to always yield. You take something that we were doing, printing out before, and you run it as a yield instead. And lo and behold, it gives you something useful back. Now we have some functional programming going on. Square maps. You can do the same kind of thing we were doing with a nested one. Now this is interesting. Nested here. There's a bit more than just a for each and a for each going on now.
I think we might have internet.
Oh, we can do our second thingamajiggy. Right, sorry. There will be a short pause as I try and find the plug.
But we can tell a joke while we wait.
Yeah, go ahead, Josh.
You don't use the one last night.
Don't use the one. Okay.
They know it now.
Yeah. Here's a better one. Two penguins are in a car. The car drives off a cliff. One penguin looks at the other one and says, "Radio? What radio?"
Waiting for the router.
As you can tell, there's no punchline.
Oh, maybe I'll come back to the router in a minute. Let's keep going, and we'll see if we can get network when we need it.
All right. Are we good? All right.
We're good. So, there's some yields. We got some more here. Now, what's going on with these? Well, these turn into, the first one, 1 to 10, for I from 1 to 10 turns into a map. Okay, gets rewritten to a map. You can see that. Thing is, if you were to do a map of a map, like in this times result case, you'd end up, instead of a whole load of times results like this one, you'd end up with a sequence of times results. So you need something else called a flat map. And so what you'll get is, if we do this, let's take that times table, and you'll see, well, now we've got a vector of vectors, right? Not exactly what we want. So we can flatten that out. I'm sure this is all teaching you to suck eggs, but believe me, it gets better.
Yeah, I mean, everybody does remember this process, right? This
Right.
discovery. as you walk through and you start to realize what these things actually are doing.
And this is, literally what happens in the compiler. It's turning that for expression is turned into these calls during the parser phase. And we'll demonstrate that. We'll prove that to you momentarily. So there you go. And basically the rules are pretty simple to follow. If you ever know it. Can I use the G word now?
You can use it.
I can use the G word?
Yeah.
Every generator, every one of these things, is a flat map up until the last one, which is a map. That's a pretty easy way to remember it. So you just go flat map, flat map, flat map, map. Super easy. Right. So I think I should let my friend Josh talk. I'll swap
All
you
right.
for the mic here.
I can't be as loud anymore. Or I guess I can. Wow. So this is your apprenticeship, right? You've walked through the land of learning forest.
My young Padawans.
Then we get to start learning, maybe I can do these things on collections, right? Like I can yield collections out. It looks like SQL.
Yeah, what about options, man?
Right, let's take a look.
Options, that's not really loopy.
Yeah.
You only got one. You got at most one thing in an option. So
right, and yet, what's the button again?
Shift and enter.
Shift enter.
It
All right.
takes
So here we have like X, Y, Z, and we directly multiply them. But then when they're in an option, you want to actually directly multiply them. So the first thing that you do, or I should say one of the things you learn to do, is use fors to actually lift the things out of the options and then run the same kind of a function on them, like multiply the three together. And when you run that, we wait a little bit, and you see that you get, you have sum 1, 2, 3, and you get sum 6. So it's doing the same function on these things, but it's kind of like extracting them out, It's not quite iteration.
Right. This is. I think this is one of the most profound lessons people learn early on. Is whenever you've got something that's some code that just multiplies x times y times z, for example, if you then have a consistent container like an option, you can always take the original code, shove it into a yield block, and then dereference the things in a for block, and it will work. That simple formula will work for all of the containers. Okay.
Right, so you're starting to build this intuition for how to lift across these crazy, type parameter things. And then we continue with that iteration, right? So if you have a none in the middle here, and we actually run this code, we know that it's safe to do so because of the way this thing is constructed. The none basically nulls out this for expression. We get a none at the end, right? It can only run that computation if everything has a value. So we start to get these more advanced intuitions, more advanced ways of thinking about this.
So then people say, well, it's still kind of a loop. It's just that option has this nature of being something that's like a collection, sort of.
Yeah.
But it's either got 0 or 1 things in. But then you say to them, but you can do things over these things called futures. Now, what's going on here? This is not. There is no way this is any longer a loop. Yeah, give it a second to import that stuff. So let's take I think, doesn't Victor Klang kill a puppy every time he sees a thread sleep in something? Oh, it's a kitten. Sorry, kittens. But it does make for a very useful demo. So we've done a quick thing here. Now, what you'll see here is that we've artificially introduced a bit of latency into our system, and we can use the for expression. Now that, hopefully, I was quick enough to say, that came back instantly. That didn't wait 10 seconds like you'd expect. It gave us back a future, but as of right now, that future is unresolved. If we execute the next one and force it to wait for it...
Yeah, hold on. Sorry.
That's
I had
all right.
to press buttons or something.
Then we get our answer back. Now, this is pretty profound, but that is in no way looping anymore. That's doing something else. Right?
You can see it, right?
Yeah.
It's the most profound number in the universe, actually.
It is, yes.
But yeah, it's not looping, and more importantly, this is actually one of the most elegant ways to do asynchronous programming, right?
Yeah.
Like we can throw computation into a completely different context, and then kind of lift these functions that were originally sequential into that asynchronous context, and we're kind of all there, right? I mean, every single talk I've seen so far, you're already past this point, right?
Yeah.
How many people don't do this? Okay.
Okay.
Cool.
we're preaching to the choir. All right, moving on. So really, and this is the philosophy, fours have nothing to do with looping at all. The only reason they're used for looping is the nature of the collections that you work with. What they really are, and this is the philosophy of a four, is you work on what's inside, you let the outside take care of itself. And you decide what the happy case is. The sad case is decided by the container, whatever that may be. And other things. The container can actually do a lot. We'll talk a bit about some of the crazy lengths we go to towards the end.
And this is one of the points, I think, of functional programming in general that I really appreciate is you focus on your business logic. Like this for... You don't care about how it does the asynchronicity, right? That doesn't matter. That's not important. What's important is I'm blending my business logic and figuring out how to talk to this service, and get the data together, right? For futures, in that case.
So we like mnemonics, and we came up with one for this. The physiology, the 3 Gs, okay?
Well, 4 Gs if you count the last one.
Yeah. So you got your generator, you've got your guards, you've got your inline assignments.
Yes, and then you have the give block, which is called yield.
Yes, so those are the 4 Gs of a for statement. Okay, next one, I think. All right, so what's a generator, Josh?
All right, so a generator is, in for, it's basically the way that you pull stuff out of context or a container, right? We know that it's not exactly a collection. But what's neat here that some people don't realize is it's, full pattern matching syntax. But the implications of that are very significant because you can do anything you can do with pattern matching, which I think we have an example of later.
If you click on the title there.
Oh, I should just click on it right away.
There we go.
Right. So a generator basically looks like this, where you extract something out of something on the right-hand side. You give it a name. You're binding it. You're giving it, how you're going to talk about it later. So with this, it's just multiplying I times itself, etc. Here we have something a little more significant. We're actually extracting a map. Well, a map is a collection of keys and values, and we can pattern match on keys and values in there, right? We are all aware of this because you've probably written code like that, which is similar to just vanilla pattern matching, right? Where it gets really interesting, I'm just going to execute all these. Where it gets more interesting is when we start using extractors. So here in the for expression, I can actually rip out the case class values, right? I can pull out their names.
Oh, there's a step that you've missed that we thought we'd throw in at this point, just an extra.
Oh.
Some people may not be aware of this, but val is actually a pattern match as well. When you say val x equals foo, that will match anything, just like a pattern match would. But you can say something along the lines of val step no comma instruction is treasure map head. And that will just pull out the 2 items from the tuple. If you give it something that it's not expecting, you can get a match error. That throws a few people the first time they see it. They get a match error out of a val. And they're like, what? What just happened?
So what we end up with then is the fact that we can actually do pattern matching in here. We can bind variables out. We can rip things really far apart if we'd like to. So here's just one of where we're checking all of the characters from Harry Potter and how old they are today.
Yeah. Does this make anyone feel old? I worked it out. The first Harry Potter book came out in 1997 and he was 11 years old. That makes him 30 today.
Yeah, and in case anyone hasn't read the books, there's spoilers in here. We apologize.
Oh, yeah.
Close your eyes, please. All right, so here's a more advanced example where actually, sometimes people use if statements in fors, which we'll talk about later, but you can actually use pattern matching to filter out how you extract things. So here we define a extractor for even, right? And we can treat this as a legit pattern match and just grab all the even values and bind them to the name x and make use of them. So when we execute this, it's just going to print all the even values from 1 to 100.
Oh, and another little extra here. Anybody not seen or not remember the binding operator? That one always throws our students when we're doing the training, the at. Basically, it takes whatever pattern match you've got on the right and sticks it in the variable on the left. Usually somebody says, what the hell is that? That doesn't look like real code.
So always name your extractors VIL, because then it looks like everything you do is evil.
All right. Okay. Guards. Yeah, let's swap over for a bit. Guards. We didn't actually rehearse the timings. We were just winging it as to when we did the handoffs. So, what is a guard? Oh, just open it. There we go. So, as well as your generators, you can have if statements, or if expressions, I beg your pardon, inside of a for. Here's an example. We are completely made up, but we're generating 1 to 10 in x and y. And then we're going to say if x mod 4 is less than y mod 5, and then another if, and these get anded together, effectively, behind the scenes. So if x mod 2 equals 0, yield x times y. Not quite sure why you'd want to do this, but there you go. You can do wacky things like that.
And all examples must be on integers for slides, just FYI. In case you were curious, it's a rule.
There's another one. This one does. This one shows you how you can OR things together. So if you the implied way that ifs are handled if there are multiple ones is it's an AND. They all have to be true. If you want to do an OR, you just stick an OR in the middle. Pipe. And Bob's your uncle. So what actually happens with these? I think this is probably where it starts to get interesting, right?
Yeah.
So, when you do this, you need something. So we've talked about map and we've talked about flat map. The guards use a thing called with filter. Now, effectively, and I think this is probably the advice I give most people, you can write a with filter to be pretty much exactly the same thing as a dot filter method. With filter is really there's a optimization that you can make to try and combine functions together, so make it more efficient.
Yeah. So historically, what happened was we had filter methods, and filter methods would eagerly create you a new collection that were filtered, right? But it turns out that that's not actually efficient. You don't want to do that. You want to delay the filtering operation until they actually do a map or something. Right. So they added with filter into the collections library and moved everything to with filter, and with filter is meant to be lazy. So filter is meant to be eager, with filter is meant to be lazy. It's meant to defer actually filtering, which is why it's called with filter.
Now, what I'll say is that, probably 90% of the custom constructs that I've used, that kind of performance worry is not a concern. So if it gets you to the solution quickly, just write a filter and worry about the optimization later. But you should know that that's why it was done. It's there as a performance enhancement. Okay, so let's take something like this, this rather lengthy thing. Oh, it seems like I lost my extra bits, my explanation, but not to worry because I can just go to the example over here. So actually, let me show you the simple way to do it. Let's have a look at these three. For expansion 1.scala. Okay. Here's a very simple for expansion, 3 generators. One of the things I can do is say Scala C-X print parser and then for expansion 1.scala. Right. And what this does is, have you guys seen this? I expect everybody's seen this, but let's show it anyway. Is it dash phases? Yes, I think it is. Yeah. These are the Scala compiler phases. Okay, this is how Scala does its work. It runs through these pretty much in order. Each one of them, well, almost all of them, take an abstract syntax tree and modify it in some way to get it closer and closer to compilation, apart from the generate JVM bytecode at the end and the original parser, which parses the source code and turns it into the AST in the first place. After the parser happens, fors have already been desugared. So we can see here that indeed you get something that says 1 to 3 flat map I, 1 to 3 flat map J, 1 to 3 map K.
So one thing that's really helpful with here, just to call it out now, if you're designing a API that's meant to be used in fors and you're like, oh, how the hell is this desugaring? Why am I getting an error? This is a good way to figure out what's going on. Now,
the desugars a lot of things, including all of the symbols, so it gets fairly hairy. When you start getting into this, you see $%, $equals, $bar, and so on.
But that's what your Java code looks like. So
I should show you the original of that one. Yeah, Scala. This was for expansion 2. So this is with a guard. And now you can see that there's the with filter that we were telling you about. This is how it desugars. Okay, there's a couple of with filters in there. It's doing the rest of the work. You can see all that there. And then I think the third one is really there to show you how quickly this becomes something you wouldn't want to write yourself, certainly. So here, this is an inline assignment. So I think maybe we should talk about those next.
Okay.
The assignment. So yes, the third thing is an inline assignment. Now this, I think, is where a lot of people, this may have a nugget of something you didn't know already. You can do anything you like in a for block, in a for setup. All you have to do is stick it in an assignment, and you can call anything you like. You can call logging, you can call printing, so on and so forth. Most of the people, or many of the people that I work with who are not Scala software engineers, they're quite surprised to find this out. They're like, but I can't log in there. And I'm like, actually you can. Just stick an underscore equals, and you can make some logging happen. You can print something out, and so on. Now, there is a gotcha here. It can affect the ordering that things happen in, so you should be aware of that. But, you know, if you just want a quick and dirty way of getting a diagnostic out of the middle of a for expression, that can be pretty useful to know about. So this is an example of why you might want to use one of those. One example, here we are making a guard on I times j times k mod 2, so is it even? And then you'll notice we do I times j times k again. That's a little wasteful, so what we can do instead is just say mult equals I times j times k, and we can use mult, and the thing is now you can use mult in the setup, and you can use it in the yield, okay, as soon as it's defined. Yeah. Good. And this desugars, this is my desugaring, if you're curious, into something like this. Now it gets kind of interesting here. Now suddenly, when you do an inline assignment, you're passing forward the last thing from the generator, right? Your k, but you're also passing forward this mult to the next thing. So just passing forward one or the other is no longer enough. Now you're passing in a tuple, and you get pattern matching for the rest of the for. Okay, this is how this desugars. That's a lot cleaner than the one that the thing now. And this is just an example of sticking a print line in the middle of it.
Which, I mean, nobody ever uses print line to debug things, so I know it's not useful. But
you'd be surprised how many bugs I found this way. It really is quite useful. All right. So where do we go next? I think that's the basics done. We can move on to the more advanced topics now.
So one thing here to remember is that fors have this implicit design principle, right? Were there any interfaces for us to use a for expression, like any specific traits or anything? No, it's loosey, right? It's by name. It's almost Pythonic.
Careful, I do see Martin back there.
I know.
He may be hunting you down.
But it's implicit. However, sometimes you actually do want to formalize. Sometimes that can actually provide value. It does limit what you can do in a for expression, but it actually can provide value. So let's just take a quick look.
Can I swap you? There we go.
Okay.
Take over, man.
All right. So we're going to formalize, right? What's the formalization of a for expression? What's the thing you need? Anyone? I mean, it's actually not on the slide. Anyone?
If there are any hands
what?
up. You do need
James Bond to formalize a for expression. Yeah. It's I have a picture of him by the computer just so I can do things formally. So you need something that's kind of like a monad, but it's a little bit further because of that with filter. You can't actually just use monads if you want to use the entire for expression syntax. But if you have something that looks like this, you can do a lot. You can still do a good bit. So a monad is a, by the way, few rants that I'm just going to throw out right now. One is, everyone says list is a monad, option is a monad, future is a monad. That's not the correct terminology, ever, okay? Future has a monad. Yeah. A monad is external to the thing, okay? So a monad is something for another type that tells you how to apply flat map, map, and those operations we saw in for.
It addresses the nature of a type, effectively.
So you could have a instance of this for list, you could have an instance for future, you could have an instance for other things, but those things have monads. So you can actually formalize this as a trait, which will tell you how to implement for and all that kind of stuff. And then what we can do is we can define, say we have an asynchronous API. This is an API to hit GitHub. Okay, I want to give a user and get me the projects that they're associated with. Give me all their pull requests for a particular project. Give me all the collaborators for a particular project, right? But I don't want to commit to the fact that this is asynchronous. I don't want to commit to how it's asynchronous. So what I do is I lift out the type that defines whether or not it's asynchronous. So normally you would write this with futures, right? I would return a future sequence of project. Instead, what I do is lift out the type. Okay? And then when I use it, I need to take in the monad for that type to know how to use these things in for expressions. I actually need to take in more for some of the things I'm doing, but this is a slide, so I can not have code that actually works. Anyway, so when I define something higher level that makes use of this API, I can now return things within this context, and I don't care what the context is. I don't care that it's future, okay? But I can still use the for expression. By the way, this code is all on GitHub. I think there was a link somewhere. This is from Intro to FP on Suereth on GitHub.
Did you? I may have blanked for a moment there. Did you mention that this way you can actually either migrate something between being eagerly and...
No, that's the next thing.
Oh, okay, sorry.
So, there's the link. Okay, I'm awesome. Sorry. Here we go. So the idea here then is, since we made it completely generic, we can actually swap out which monad we use. So if you use the identity monad, this runs sequentially. It runs in process. It means you can write tests without future data wait. It means you can actually not have tests that randomly time out and die, right? Which is a beautiful thing. But when you want to be synchronous in production, you would use future, right? You keep it asynchronous, you get all the benefits of that. But you can test the simple logic in a simple way. So this abstraction actually allows you to change the context through which your functions run. Right, that's step one of your aha moments.
So some of the other types that have monads, and we can click on these to bring them up. Either, unfortunately, we are running. Oh, right now we're running 2.11. We haven't got the 2.12 yet, which has a new either, which is right biased at the moment. I believe there's some negotiations happening, but either has a monad for the right side and the left side, and you choose one or the other right now. So here is an example of the either string or an int, and by saying from e1.write and e2.write, you get back a right, assuming they are both right. If one of them is left, the left will carry through. This is the unhappy case for either, is whichever side you're biasing towards. If it's one of the other side, that will just carry through. It will short circuit to the first one of those and give that back to you.
And then there's a few other instances of this where, like, Scholastic has something called OR, where you can have an either of like a string or an error message. It also has monadic behavior, where you can essentially keep these things in for expressions. The cool thing about that is you can have code which returns errors. Or do I have to?
There's an accidental paste in there. Just get rid of that X at even, and things will be good, I think.
I am good at pasting things. All right. Here we go. So here you can have a notion of parsing, right, which returns an OR, where it's either something or an error message, string or error message. And now we want to parse a person from input. So we pass in the input name and the input age, and both of these could be something or an error. For the purpose of our business logic, we actually don't want to care about errors until we want to care about errors, right? That's always the case. That's one of the frustrations of checked exceptions, is I don't want you to tell me about errors until I care about them, and then I want to care about them, right? So we try to defer that a little bit. So here we know there's a possible error, and this will actually aggregate the errors across things, but the for expression lets me just focus on my business logic for person and let that stuff kind of aggregate later.
And so OR is from Scholastic, which is Bill's library. By the way, Bill, thank you for the example. We ran out of time, so we pinched yours. And I told him that last night, and he said, oh, I pinched it from somebody else anyway. So, but one of the things about that I think is interesting about for, if you can just go up just a tiny bit, is that OR is left biased, which is sort of bucking the trend of right bias disjoint unions here. But the thing that is kind of the saving grace, it reads very nicely. When you're writing the code, person or error message sounds better than error message or person. It's like a glass half full, glass half empty kind of thing. What's your primary focus here? Do you want the person or do you want an error?
Yeah, and so there's also an alternative like this. Do we have the type level stuff? Yeah.
Yep.
Oh, this is a different monad, but there's another thing like for called validation validation NEL, which stands for NEL. No, not I know. Yeah. Not found cats.
There's probably an add resolver. Oh no, we have no internet. I haven't set it up yet.
So we can't do this
imagine
example.
This works.
But imagine this works. You can also do this.
Oh, it is. Well, I haven't actually. I never got through to the point where I hooked it up.
We're not going to bore you guys anymore with setting up the internet. Sorry. So here's an example that uses the state monad. Okay. So the idea behind this is I have a bunch of code that is actually super contextually dependent on state. Super contextually dependent. But I want to have independent functions that I can test where I don't have to like super mock out everything. I just want to say, here's your initial state, go run, and I want this output back. But in production, there's going to be lots of state that gets passed around, and it's really confusing. How do you do this in a functional way? Use something known as the state monad. So here is a state monad that basically gives me IDs back. Okay, it's a monotonically increasing ID. So I have this next ID function, which returns an integer, essentially, out of the state monad. And the way that's implemented is you take the current integer in state and you return, +1, or you return it, and then you bump the current, internal value. And then when I want to write a program in this monad, I can just say, give me the next ID. I want 3 IDs. I'm going to yield them all into a thing, and I get back a staged program in the state monad. And then I can run that, and you would actually see it would be like 1, 2, 3. Or sorry, it'd be 1, 2, 3 because we start at 1. But if I pass 0 as the state, you'd get 0, 1, 2, right? So it makes it a little bit easier to test things if you're super dependent on state. All right. And that was the end of that notebook, right?
By the way, John, I don't believe. How long have we got? 1:30. Okay, we're doing good.
Sweet.
We're doing good.
Okay.
Quick one of the ARM resources, because I think this is Josh's library. It's not that well known, but it's very, very nice.
Yeah, so this is a library to just make dealing with Java a little bit easier. Java has this notion of something called a closable, right? And you want to make sure when you're done with the computation that things get closed. This is a notion from in C++ you have something called resource releases destruction. In Java you have absolutely nothing at all to help you.
Say it again.
You have absolutely nothing.
Say it again.
At all. What you do is you have a try finally block with a try catch in your finally because that's cool. Yeah, so what we can do better, right? We have functional programming. There's a notion of something called the loaner pattern, where essentially you keep the access to a resource within a function. But we can do better. We can actually use monads. We can keep the access to resource within the monad. And so we have this managed thing, which can take resources from Java, and inside of the for expression, you can safely access them, and outside of the for expression, they're closed. It keeps track of errors and exceptions and will lift them up for you so you can do things. This is a loopy version, right? Because this is dirty evil code. Yay. I love writing dirty evil code. This is actually the stuff I would write in SBT. Anyway, this is basically just reading from one file to another in an efficient way with a buffer. This is one of the best ways to do it in Java unless you do scatter gather, which actually isn't really efficient anymore. Given the actual topology of hard drives. Yes. Okay, so anyway, that's the idea behind ARM. It can actually support even transactions and things like that if you're stuck in EJB, which I was when I initially wrote ARM, so yay. Okay,
so now we get to the moving into the darker side,
right.
As you can tell from Chad Vader here. There was this day that Chad Vader decided he wanted to mix his monads, and this is the result. He doesn't look very happy, does he?
Yeah, so don't mix the French fry monad with the Coca-Cola monad, just FYI.
The force was not strong with him on this day. So let's see what happens when we try and do this. This is one of the first stumbling blocks that we find our students hit. So here's a kind of setup here, just so you know. There's a passenger, there's a carriage, there's a train, and there's a route. The The route may have a train on it or may not. The train has a list of carriages. The carriages have a list of passengers, and the passengers may or may not have a cell phone number. So if we want to find all of the cell phone numbers for people on the train, let's get this going, get this set up. Oh, thank you. Yep, because I got this one. Right. Now, what you might think you can do, and many people do, is they think that you can just do route from routes, active from active route.active train, carriage from active carriages, passenger from carriage passengers, number from passenger cell phone number. And you look at that and you're like, well, yeah, that's kind of what I want to do. I want to work on the things inside. But then you try and compile it, and you get this. You get a, list string, but required option in carriage from active carriages. And the problem is that you are mixing the types here. Option is not a sequence. You're starting with a sequence. Actually, the problem is, and this makes it even worse, there's an implicit promotion of option to sequence that will be applied in some situations. So if you do about half of this, in particular, if you just said for passenger from carriage passengers, and then number from passenger.cellphone number, that would work, because you're starting with a seek, and the option can be turned into a seek just in time. So that works. But the problem here is that line 2 and 3 in the for setup, the active is an option, but then after that you're trying to do a sequence. And so now you're trying to flat map. If you remember our flat map, which has a very specific type signature, you're trying to shoehorn in a different type, and it won't work, it won't compile. So how do you fix this? Well, and this is just an example of that. The reason it works this way is that particular one is, it's sort of evaluated inside out because of the scoping. And once it hits active carriages, at that point it's got an option, but it tries to flat map over a sequence, and that causes the problem. So how you can get around this? Well, in this case, it's a pretty simple fix, and we recommend this for everyone. Just stick a to-seek, an explicit to-seek on all of the options. Whether it needs it or not, it's quicker just to not think about it. Stick the to-seek on there, and you're good. Okay? Then everything's a sequence. Life is good. What about if we have something a bit more tricky, like a future of a sequence? Okay? Same problem. Here's our future, list of numbers. It has a list inside. It's a future of a list of ints. We can get the numbers out of the future. That works. But when we try and get the num from the numbers, that's trying to flat map a sequence into a future, and that won't work. Type signatures don't match up. So what can we do? Well, in this case, it's an easy fix. We have our friend traverse on future, if you know it's there. What it does, and in this case, actually, I should mention, didn't say this before, we're actually doing a future, then a list, and then another future. The setup for this is that we've got a future of integers that's been got out of a database, and then we're doing a calculation, and it's a very complex calculation that takes a long time. So we return a future of it, okay? And what we want to get back is just a single future of the items that have been squared. So what we can do is we can use this thing called traverse, and what traverse does is kind of maps the function over the items inside the sequence, and then flips around the fact that you've got a sequence of futures and turns it into a future of sequence automatically for you. So it's a very nice operation for that.
If you want to learn more, there's a paper called The Essence of the Iterator Pattern. That's actually a really good read. Traverse is pretty amazing in terms of what you can do. So recommend looking that up.
So what about crossing the monad streams? Well, let's see.
Should you cross them?
Should you? I don't know.
We've never tried.
What about if you've got a future of an option? Well, let's have a look. Let's see some M and M's.
Anyone familiar with the library M?
Now I'm going to need the network.
I'm really sad that Alyssa
Tell a joke.
isn't here. Yeah, okay. Few people. So it's basically a library to help you mix monads way more elegantly than a bunch of other things.
Is it Scala World I need? Oh, yes, Scala World. Got it. Oh, yeah. Please don't use it all.
Yes.
We've just got network. reged center with an RE.
Okay. All right. So, but basically, what it does, it's using some simple techniques, but you're lifting all the computation that you do. So every time you do that for expression, you have to lift it into this this type you define of all the monads you want to mix for every single generator. But it will automatically kind of figure out how to take an option and turn it into a future of option. It'll automatically figure out how to take a future of X and make it a future option X, right? And all that for you. So if you're doing something complicated where you need these nested monads, it actually really cleans up the syntax significantly.
It's not looking happy. Oh, look at that.
We might need to just use the slide. Or are we on?
I think we'll be all right now.
Okay.
Let's see.
We just have to download a library. It won't take long, I promise.
It actually has the library, but due to the... no.
Yeah.
Something's unhappy still. Oh, well. Maybe it'll work for the... yeah, it's not happy.
In terms of other dad jokes, at some point someone needs to make a library called Dogs. Just FYI. I think Miles was the perfect candidate. What's the library they call Dogs?
It's called Dogs.
Which one is it? Stu O'Connor. Oh, okay. Okay. But if you mix cats and dogs, then you get mass hysteria, which is the library that... Oh, well.
All right, one last go, just in case. No, we're not going to be lucky today. Maybe the video will work. What I will say is all this in GitHub. We'll stick the link out once I've uploaded the latest version, which is only on my laptop right now.
Let's talk through the slide.
Yeah,
I think there's the code's on the slide.
Sure.
So there's at least an example here.
There we go.
Okay, so this isn't an in-depth example like we had in the Jupyter, so I apologize. But essentially here we have we define the mixture of monads that we want, right? We have a future of option of base, right? And we want the semantics that, if one thing is a none, we don't fall through, but the futures all happen asynchronously and all that kind of junk. So you define type E, which is your mix, and it always extends from this base type in M. And then anytime you want to put something in the for expression, you have to lift it into this M type, okay? So when you pass an option of 42, what you get out of this is something that will eventually be like a future of option 42, okay? It's not quite that, but like practically that's what you're thinking. And then when you're done, you call .run on the result of this for expression, and you get back, a future of option of something, and then we have to do the await.result because it's asynchronous, and yay. Cool.
So, I must say, Daniel's done a spectacular job. I think it's about the nicest kind of solution to the kind of monad transformer problem that I've seen. But I'm going to go back and make my pitch here. So when I was growing up, I used to hero worship my dad, don't we all? And particularly when he got the power tools out. He was like awesome with the power tools. And I really wanted to use the electric drill. And he never let me use the electric drill. He always gave me the hand drill. I think what he said was you should really understand the process and the materials before you use an electric drill. I think what he actually meant was I don't want you drilling a hole in your hand. But the thing is that I have a great drill at home. I still have a hand drill. Sometimes I just pull it out when I need a little hole in a bit of wood. Okay, you get much more control with it. And the point of all this is that if you're doing a whole bunch of really hard work, you might need monad transformers. In my experience, complexity is rarely battled by adding more complexity. Okay, sometimes it's good to go back to the basics and see if you can simplify things. So that example we just had, let's do this. Let's take a future of option of future. As an added bonus, this will work because it doesn't require any dependencies. And we can't mix options and futures, okay? The flat map doesn't work. But what we can do is something like this. A 4 within a 4. Who'd have thought it? So in the for block, we can say for x from f1, for z from f3, z from f3, sorry, forget the audience. And then res, inline assignment, equals for y from O2, yield x times y times z. Super
what was that
simple.
letter again?
Z.
What?
Z.
What?
Z's dead, baby.
Okay.
So now you yield the result at the end. Everything's easy. I think that's pretty readable. Okay? It doesn't look magic like the other one. It's not, maybe it's cool, but it's very simple. it's probably a little more optimal to run as well, if that matters to you.
We should actually clarify that it is more optimal.
It is more optimal,
M
yes.
does have some overhead right now. So, I mean, they're going to try to improve it, but there is overhead. So, however, if you imagine that code with, say, 3 monads, that's when it starts to get to the point where you might want to think about the trade-offs, right? Anyway, sorry.
Another thing you can do, okay, a lot of people choke over this because they don't like the 4 within a 4. So don't put the 4 within a 4. Split it out. Multiply options together in one function. Okay, it's now testable. Super easy to understand. Everyone can understand that. Everyone can understand the second one. You just get the V1 and the V3. You stick them into sums, basically promote them to sums in this case, and then you call multi options. Super easy. There's plenty of alternatives here.
Yeah. So basically, what you're doing in your code is. Did I turn this off? No, it's on.
Okay.
What you're doing in your code, if you think about it as each of the layers of that monad stack that we had being a conceptual layer of your domain, right? You write functions for each layer explicitly, as opposed to trying to implicitly lift everything out of it. So it's akin to, oh no.
How loud's it going to be?
We have the internet.
We haven't done this yet. It could be very loud.
Okay. There are things which are not monads.
I love this picture, man.
I know it doesn't make any sense, but there are. So this is a picture of Darth Vader trying to Brita filter the ocean.
It's a desalinization plant.
Yeah.
A very low-tech one. Desalination. That's the one.
All right, so sync. How many of you guys know what sync is? You pass values into it. Like I want to have a sync of bytes, which could be a file, and I just shove bytes into it, right? Can you stay on that slide? Sorry.
Oh yeah, sorry.
So sync is actually it's not a monad. It has that thing to it, which we'll talk about in a little bit. But what we might want to do is we actually have a sync of, say, bytes for a file. But I don't want to, in my domain logic, I actually have some sort of type, like users or addresses or something, and I want to save it out the sync. But I'm starting with a sync of bytes, and I want to get to a sync of users, except I need a function that goes from user to byte. And if I try to write map for that, I actually get byte, and I need to go to user. So it's like the opposite, right? Like the arrow is in the complete wrong direction. But wouldn't it be kind of cool?
Doesn't that make it a co?
Shh.
Sorry.
We'll talk about it in a little bit. Right. So here's an example. I have like a standard out sync, right? That takes strings and just writes them out to standard out. Wouldn't it be kind of cool if I could have a for expression where I say, oh, actually I want to start with user, and then I'm going to write a for expression that eventually yields that string. And it's going to actually invert my arrows for me automatically and convert that sync into a source, essentially. And then I get a sync out the other end of sync of user. I can actually do this. This code runs.
Let's see. Does it?
I hope so. We don't have to import anything.
Will it blend?
Don't look at the ugly code. I'm sorry. This is dirty.
Yeah, this is just the setup. Ignore the man behind the monadic curtain.
So here's the actual code with user. We have a list of user. So we have Josh from Pittsburgh and Dick from Morgan Hill, which, if you don't know, I'm from Pittsburgh and Dick's from Morgan Hill. Technically, I'm from Mars, Pennsylvania. It's a town.
Oh.
The post office has Martian dolls. Did we forget to compile it?
No, I just apparently didn't shift-click on it properly.
Okay.
Stupid user error. Or there's something else wrong with it right now. Oh, well, the code's up on GitHub. You can run it later.
Okay. Oh, no,
it did. It just took a really long time. There we go.
It's cool. It's simple code, I promise.
There we go. Woohoo!
Right. So now you can see it outputs Josh because we have that if filter for lives in Pittsburgh. And what we're doing is we're taking advantage of this notion that monads and comonads and functors and cofunctors are actually duals of each other. And so basically, when you have a function where like 4 expressions go this way, but the dual goes that way, however, we can still abuse the fact that you can define a function from here to there and kind of flip it around in fun ways, which is what we're doing. So that's duality. There are things which are not monads, but that doesn't mean you can't still use 4-expression syntax with them. So that's just a little dirty trick for that.
By the way, the force is like duct tape, you know that? It has a light side, a dark side, and it binds the universe together.
That's a good point. That's a good point. All right. So anyway, with that, we hope that you really, really, really attack 4 expressions really hardcore. So long, and thanks for all your 4s.
And may the 4s be with you, always.
Oh, do we have the GitHub link for people?
Not yet, but I'll stick it out on... I'll stick it out on the Scala world. If you go there right now, it's got like 3 things in the notebook because all the rest is on my laptop, but it will be pushed to GitHub very shortly.
It's github.com/dickwall/use the 4s, Luke.
Yes.
Okay.
Thanks. All right, cool.